Somewhere in a physics textbook, on a page most people will never read, there is a single number. And that number is wrong. Not slightly wrong. Not wrong in the way a weather forecast is wrong. It is wrong by a factor of 1 followed by 122 zeros. To put that into something a human brain can actually hold, there are roughly 10 to the 80 atoms in the entire observable universe. Every atom in every star, in every cloud of gas, in every planet, in every grain of dust drifting between galaxies. The error in this single calculation is 42 orders of magnitude bigger than that. The mistake is more atoms wrong than the universe contains. Now here's the thing that should stop you cold. The exact same theory that produces that catastrophic prediction, the same equations, the same toolkit, the same machinery scribbled on the same blackboards, also produces a different prediction. A prediction about the magnetic behavior of a single electron. And that prediction is so accurate that if you used it to measure the distance from London to Sydney, your error would be smaller than the width of one human hair. One theory, two predictions. One of them is the most precise statement humans have ever made about anything. The other is the worst. And nobody, not the physicists who built it, not the mathematicians who criticize it, not the philosophers who circle around it, nobody can fully explain why both of those numbers come out of the same theory. If you stay with me, I'm going to walk you through exactly what's happening here. Because the answer that's quietly been forming inside the physics community over the last 40 years is more unsettling than a wrong number. The answer is that the entire theory we've been calling fundamental, quantum field theory, the bedrock of modern physics, might not be fundamental at all. It might be a skin, a surface, a cover sheet stretched over something deeper that nobody has ever seen and that we may never be able to see directly. So get a drink, get comfortable, hit subscribe if you haven't already, because once you've followed this all the way down, you are going to look at the word reality differently. I promise you that. Part 1. The experiment that was supposed to break physics. For more than 2 decades, there was a single experiment that physicists kept pointing at when they wanted to talk about the future of their field. It was running quietly at Brookhaven National Laboratory on Long Island in the late 90s and early 2000s, and it was doing something that on the surface sounds incredibly boring. It was measuring how a particular subatomic particle wobbles inside a magnetic field. The particle is called the muon. You can think of it as the electron's overweight cousin. Same negative charge, same spin, same response to electromagnetic forces. The only meaningful difference is that the muon is roughly 207 times heavier, and it lives for about 2 millionths of a second before it falls apart into other particles. That's it. That tiny window of existence, just long enough for the muon to spin around a few thousand times in a strong magnetic field, turns out to be one of the most sensitive scientific instruments humans have ever built. Not built into something. The particle itself is the instrument. Here's why. When any charged particle with spin is dropped into a magnetic field, it doesn't just sit still. It precesses like a spinning top that's been knocked off its perfect axis. The rate at which it precesses depends on a number physicists call the G factor. And in the simplest possible version of physics, where particles are just little points and nothing weird is happening around them, that G factor would be exactly 2. Clean, round, boring. Quantum mechanics ruins that. Because according to quantum field theory, the empty space surrounding the muon isn't actually empty. It's seething. It's full of what physicists call virtual particles, pairs of electrons and their antimatter twins flickering into existence and vanishing again, photons appearing out of nothing, quarks and antiquarks dancing in and out of the void. None of these things are stable enough to detect directly, but they're real enough that the muon feels them as it spins. They tug on it, they push it, they warp its magnetic response by a tiny, almost imperceptible amount, and that warp shows up as a deviation. From the clean number 2, the deviation is called G-2, and measuring it precisely lets you essentially X-ray the vacuum itself. For decades, the experiments and the theoretical predictions disagreed, not by much, about 2 parts per million. In most fields of human endeavour, agreement to within 2 parts per million would be celebrated as a miracle. In particle physics, where you regularly get agreement to 12 decimal places, a discrepancy of 2 parts per million is a screaming red alarm. It's a crack in the wall. And if you stare at a crack in the wall long enough, you start to wonder what's on the other side. What might be on the other side, theoretically, was extraordinary. Supersymmetry, a framework that doubles the number of particles in nature, predicting that every particle we know has a heavier partner we haven't yet found. Hidden dimensions, new forces, a whole dark sector of physics that could finally explain why the universe seems to be 27% made out of matter we cannot detect. Any of that could potentially be hiding inside a 2 parts per million crack. So when Fermilab, the American particle physics laboratory outside Chicago, took over the experiment in the 2010s, actually shipping the giant 50-foot magnetic ring from Brookhaven on a barge down the East Coast and around to the Mississippi, a journey that took weeks and went viral on social media, the entire physics community held its breath. New results came in 2021. The crack was still there, bigger than before, with tighter error bars. Theorists scrambled. New papers appeared every week proposing what kind of new physics could be hiding inside that gap. Then came 2023. More data, tighter bars. The crack held, and then in 2025, the final combined result dropped. And alongside it, a new generation of supercomputer simulations of the strong nuclear force. The calculations theorists had been waiting on for years to firm up their prediction. And when the new theoretical number was placed beside the new experimental number, the crack closed. The two values lined up, not perfectly, but well within the combined uncertainties. There was no anomaly anymore. There was no doorway. There was just one more case of the standard model of particle physics, the framework physicists have been quietly trying to break for 50 years, being right again in the most boring way it could possibly be right. The press releases used the word triumph. But if you watch the seminars where the physicists actually presented this, you could see something else in their faces, a kind of fatigue, because this was supposed to be the one. After every other anomaly had collapsed back into agreement, this was the experiment that everyone had bet would finally crack open, and instead the egg got harder. Now sit with this for a second, because I want you to feel the shape of what's been happening. Every single time for the last 40 years that physicists have thought they caught the standard model lying, every single time the lie has evaporated under closer examination. The Higgs boson, predicted in the 1960s, was found in 2012 at exactly the mass theorists expected. The neutrino, originally predicted to be massless, turned out to have a tiny mass. But the fix was so small, the framework barely flinched. The proton radius puzzle, the B-meson decay anomalies, the muon G-2. One by one, every threat to the standard model has dissolved. At what point does that pattern stop being reassuring and start being suspicious? Because here's the thing, we know the standard model is wrong, or at least we know it's incomplete. It doesn't include gravity. It doesn't explain dark matter. It doesn't predict the energy of empty space. It has roughly 25 free parameters that have to be measured by hand and plugged in, with no theoretical justification for the values they take. By every reasonable definition, It's an unfinished theory. So why does it keep passing every test we throw at it? That's the puzzle we're going to live inside for the next 2 hours. And I think the answer that's been quietly emerging in physics seminars and review papers for the last 40 years, is one of the most beautiful and unsettling ideas in modern science. But to understand it, we need to leave the experimental floor and go somewhere stranger. We need to talk about the calculation that put physics into this position in the first place. The number that's right to 12 decimal places. The miracle that nobody can fully explain. Part 2. The 12 decimal miracle. I want you to try to feel a number with me, not understand it intellectually. Feel it. The current best measurement of the electron's magnetic behavior agrees with the prediction made by quantum field theory to roughly 1 part in 1 trillion. 12 decimal places. To put that in physical terms, imagine the distance from one side of the United States to the other. Roughly 3,000 miles. Now imagine measuring that distance and being off by less than the width of a single human hair. That is the precision we are talking about, not a marketing claim, not a rounded headline. The actual peer-reviewed agreement between the equations on the page and the meter readings in the lab. There is nothing else in human knowledge that comes close to this. In biology, theoretical predictions are usually celebrated when they get within a factor of 2 or 3 of the experimental value. In chemistry, the gold standard is parts per million. In medicine, you're lucky if drug interactions can be predicted within a factor of 10. Even in general relativity, the other great pillar of modern physics, Einstein's theory of gravity, the most precise tests, like the timing of pulsars or the comparison of atomic clocks at different altitudes, top out at around 1 part in 10,000. Impressive, beautiful, off by orders of magnitude compared to what quantum field theory does for the electron. And the electron isn't a fluke. Quantum electrodynamics, the part of quantum field theory that describes how electrons and photons interact, has been making predictions like this since the 1940s. The Lamb shift, a tiny adjustment in the energy levels of hydrogen caused by the electron interacting with the empty space around it, was measured precisely in 1947 and matched the theory beautifully. The Casimir effect, a measurable force that appears between 2 metal plates placed close together in a vacuum, caused entirely by quantum activity in the supposedly empty space between them, has been confirmed to high precision. Every single prediction the theory has ever made about the electromagnetic force has come true. Now here's the part where it stops being a triumphant story and starts being a strange one. The way these calculations actually work is bizarre. The technique is called perturbation theory. You start with the simplest possible interaction. An electron emits a photon, or absorbs one, and you calculate that. Then you correct it. You imagine that electron emitting a photon, but along the way the photon briefly turns into an electron and a positron pair, which annihilate back into a photon, which then gets absorbed. That's a more complicated process called a one-loop correction, and it adjusts your simple answer slightly. Then you go to 2 loops, 3, 4. Each level of correction involves more and more virtual processes happening inside the calculation. By the time you reach the level of precision needed to match modern experiments, you are summing up tens of millions of individual diagrams, each one representing a possible quantum process inside the interaction. Single calculations at this level can take international teams of physicists years to complete and require some of the largest supercomputers on Earth. And it works. Each new level of correction comes out smaller than the one before it. The series appears to be converging. The numerical answer creeps closer and closer to the experimentally measured value, and it keeps doing so. Decimal place after decimal place after decimal place. Now I want to tell you the thing that almost nobody outside the field talks about, because if you only learned what I just told you, you'd think quantum field theory was a beautiful, well-oiled machine. It isn't. The mathematical foundation that this whole apparatus sits on is, by the standards of pure mathematicians, broken. The series I just described, the one that produces the 12 decimal places of agreement, does not converge. Not in the technical sense. If you were to keep adding terms forever, all the way to infinity, the series would not settle on a final answer. It would diverge. It would explode. It would turn into nonsense. Mathematicians have a name for this kind of series. They call it asymptotic. The terms get smaller for a while, and then at some critical point they start getting bigger again, and they keep getting bigger forever. The reason quantum electrodynamics gives the right answer is that physicists have learned to stop adding terms at exactly the right point, the point just before the series turns ugly. Stop too early and you lose precision. Stop too late and the answer starts to drift away from reality. There's a sweet spot, and astonishingly, the sweet spot for the electron magnetic moment calculation puts you at 12 decimal places of agreement with experiment. 12 decimal places of perfect prediction, extracted from a piece of mathematics that, taken on its own terms, has no right to give a sensible answer at all. I'm not exaggerating this. The man who proved the series must diverge. Freeman Dyson, one of the great physicists of the 20th century, published the proof in 1952. His argument was almost philosophical. He pointed out that if the series did converge, it would have to converge for slightly modified versions of the theory too. But if you flipped certain signs in the equations, you'd be describing a physical universe that couldn't exist. A universe where empty space would spontaneously explode into infinite energy. Therefore, the series in our universe must also be divergent. The calculation produces miracles, but only because we know when to stop calculating. And nobody, not one person, has ever produced a fully rigorous mathematical version of quantum field theory that doesn't have this problem. The theory we use every day to land predictions inside the width of a hair across a continent is, by the standards of mathematicians, unfinished. Or worse, wrong in principle. Take a breath here, because I want you to hold both of these things in your head at the same time. The most successful predictive framework in the history of human civilization, and a foundation that several of its own architects have publicly admitted they don't believe is real mathematics. Both. Simultaneously. How? How does that even happen? To answer that, we have to leave the experiments behind and walk down into the basement of the theory itself. We have to talk about the move that physicists made in 1947 to make any of this work in the first place. A move so questionable that the man who invented it called it, in print, a shell game. Part 3. The Shell Game. In the years immediately after World War II, theoretical physics was in a quiet panic. The framework for quantum electrodynamics had been written down. The basic equations were on the page. And when physicists tried to use them to calculate anything beyond the simplest interactions, the calculations exploded. Literally. Every single integral that should have produced a finite answer for the electron's properties returned infinity instead. The mass of the electron, when you included its interaction with its own electromagnetic field, infinity. The charge of the electron, when you accounted for vacuum effects, infinity. The energy levels of hydrogen, when you tried to be precise about them, infinity. And these weren't computational accidents, they weren't bugs in someone's algebra. The infinities were there in the structure of the theory, baked into the equations from the start. Some of the smartest minds of the era, Wolfgang Pauli, Werner Heisenberg, the men who had built quantum mechanics itself, openly considered the possibility that the whole framework would have to be thrown out and started again from scratch. Then a procedure emerged. It was developed independently and almost simultaneously by 3 young physicists working separately, Richard Feynman in the United States, Julian Schwinger at Harvard, and Shinichiro Tominaga in post-war Japan. They would all share the Nobel Prize for it in 1965. The procedure was called renormalization. Here's what it does. The infinities that appear in the calculations, it turns out, can be sorted into a small number of categories. There are infinities that appear in calculations of the electron's mass, infinities that appear in calculations of its charge, a few others in specific places. The trick of renormalization is to notice that when you finally calculate something physically measurable, like an energy difference between two states of hydrogen or the magnetic moment of the electron, the infinities from different parts of the calculation cancel each other out. They subtract. And what's left when the dust clears is a finite number that matches experiment. Mechanically, the procedure goes like this. You start with what physicists call the bare parameters of the theory, the underlying mass and charge of the electron before any quantum effects are accounted for. These bare parameters, in the calculations, are infinite, officially, on the page. You then absorb the infinities from your calculation into these bare parameters. And finally, when it's time to compare to experiment, you replace the bare parameters with their measured physical values, the values you actually get from the lab. The infinities never appear in the final answer. They've been hidden inside definitions you never have to look at directly. It works. It works ridiculously well. Every prediction you've ever heard about quantum electrodynamics comes from this procedure. The 12 decimal places, the Lamb shift, the Casimir effect, all of it. And the men who invented the technique never fully believed in it. Feynman was the most honest about this. In a popular book he wrote near the end of his life, called QED, he explicitly described the renormalization procedure as a shell game. He used the words hocus pocus to describe it. He wrote that the procedure had not been mathematically legitimate, that the way the infinities were cancelled was a kind of trick, and that he didn't believe quantum electrodynamics was logically self-consistent. This is the man who invented the procedure, who won the Nobel Prize for it, who built much of modern physics on top of it, telling general audiences, in plain English, that the foundation might be rotten. Paul Dirac, who had laid down the original equation describing the electron, and who was one of the founding fathers of quantum mechanics, went further. He refused until the end of his life to accept renormalization as legitimate physics. He described it as ugly. He pointed out that any procedure that requires you to subtract one infinity from another to produce a finite answer cannot possibly be a complete theory of nature. He spent the last 2 decades of his career searching for an alternative. He died in 1984 without finding one. And yet the procedure worked. Every experimental test came back yes. Every prediction confirmed. The discomfort never went away. But the success kept compounding, year after year, decade after decade. Eventually, an interpretation of what renormalization was actually doing started to take shape. It wasn't a shell game, the new interpretation suggested. It was something deeper, something honest. The bare parameters that produced infinities weren't really the parameters of the theory at all. They were the parameters of some unknown deeper theory that we were trying to describe by force, using a framework that wasn't designed to handle it. The infinities were a symptom. They were the theory's way of telling us we were pushing it past its valid range. And the renormalization procedure was, secretly, a way of admitting our ignorance, sweeping the high-energy mystery into a pile we never had to confront, and getting honest, finite, low-energy predictions out the other side. That interpretation has a name. It's called effective field theory. And once you understand it, it changes everything about how you think about modern physics. But before we get there, I want to show you one more crack in the foundation. Because renormalization isn't the only place where the math goes wrong. The very framework that everyone uses to write down a quantum field theory in the first place was proven 70 years ago to be mathematically inconsistent. And almost nobody outside specialized seminars talks about it. Part 4. The theorem everyone ignores. In 1955, a mathematical physicist named Rudolf Haag published a paper. The paper proved, with full mathematical rigor, that the standard way physicists set up interactions in quantum field theory cannot exist as a self-consistent mathematical object. Read that sentence again, slowly. The standard way physicists set up interactions in quantum field theory cannot exist as a self-consistent mathematical object. This is not a controversial claim. It has not been disputed in the 70 years since. It is in textbooks. Mathematical physicists know it. Working physicists, in their day-to-day calculations, simply ignore it. The result is called Haag's theorem, and the cleanest way to describe what it says is this. When physicists calculate scattering processes, what happens when two particles collide, they almost always use a mathematical setup called the interaction picture. You imagine that, far in the past and far in the future, the particles are moving freely without interacting. Then you imagine that, in some middle moment, you switch on the interaction. The free-moving particles get tangled up with each other, exchange forces, and then disentangle and go on their way. The whole calculation is set up to compute what happens during that middle period, given clean assumptions about the past and future. Haag proved that, under the actual mathematical assumptions of relativistic quantum field theory, this construction does not exist. The free version of the field and the interacting version of the field don't live in the same mathematical universe. They cannot be related to each other by the kind of transformation physicists assume when they switch the interaction on and off. The whole interaction picture, the basic move that almost every quantum field theory calculation in the world is built on, is mathematically illegitimate. So how do physicists get away with using it? Pragmatism. They know the theorem exists. They know the foundational move is technically broken. But they also know that when they apply the procedure carefully, using physical cutoffs, renormalization, and other tricks, they get predictions that match experiment to 12 decimal places. So they do it anyway. The mathematicians grimace, and the physicists shrug, and the predictions keep coming out right. There's a famous quote, repeated in slightly different forms by different people, that captures the mood. Something close to, in physics, we use mathematics that mathematicians wouldn't recognize to make predictions that experimentalists couldn't dream of. And there's more. There is, sitting in the records of the Clay Mathematics Institute, a list of 7 of the most important unsolved problems in mathematics. They were announced in the year 2000. Each one carries a $1 million prize for whoever can solve it. One of those problems, the one called the Yang-Mills existence and mass gap problem, sits directly underneath the standard model of particle physics. Yang-Mills theory is the mathematical structure that describes the strong nuclear force, the force that binds quarks into protons and neutrons. The Clay Institute's challenge is essentially this: prove, with full mathematical rigor, that quantum Yang-Mills theory exists in 4 dimensions and that it has the properties physicists assume it has. 26 years later, the prize has not been claimed. Nobody has proved it. The mathematical foundation of one of the 4 fundamental forces of nature has not been rigorously shown to exist. We use the theory every single day. We compute with it. We confirm its predictions in experiments at the Large Hadron Collider. And strictly speaking, mathematicians haven't yet been able to prove the thing we're computing with is even self-consistent. When I tell you that the foundations of modern physics are unfinished, this is what I mean. It's not vague. It's not philosophical. There is a literal $1 million bounty on a piece of the foundation, and it's been sitting there, unclaimed, for over a quarter of a century. So here's where we are. The most successful framework in the history of physics is sitting on a foundation that includes a divergent series, an officially illegitimate setup procedure, a concept its own inventor called a shell game, and an unsolved $1 million problem. And yet it keeps producing the most accurate predictions in human history. How? How does any of this work? To answer that, we have to step back and ask a much simpler question. A question I think most people have never had a chance to really sit with. What does quantum field theory actually say the universe is made of? Because the answer is not what you've been told. Part 5. The universe is not made of particles. If I asked you what the universe is made of, you'd probably reach for the picture you learned in school. Atoms made of nuclei surrounded by electrons. Nuclei made of protons and neutrons. Protons and neutrons made of quarks, a nested hierarchy of progressively smaller balls rattling around inside each other. That's the picture almost everyone carries. It's wrong. Or rather, it's a useful approximation that breaks down completely once you actually look at what quantum field theory says is going on. According to the theory that produced the 12 decimal places of agreement we've been talking about, the universe is not made of particles at all. It's made of fields. A field, in this technical sense, is a kind of structure that exists everywhere, all at once. It has a value at every single point in space. The electromagnetic field is the easiest one to picture because we already think of magnetism as something that fills space. But quantum field theory says that's just the beginning. There is also an electron field, a field that exists everywhere in the universe, inside your body, inside the sun, inside the empty space between galaxies. Every cubic centimeter of reality has the electron field in it, doing something. There's a separate field for each kind of quark, a field for each kind of neutrino, a field for the Higgs. Roughly 17 fundamental fields in the standard model, all of them everywhere, all the time. What we call a particle is just a localized vibration in one of those fields. An electron is not a tiny ball traveling through empty space. It's a ripple, a packet of organized disturbance in the electron field, propagating from one region to another the way a wave moves across the surface of a lake. The water doesn't actually travel with the wave. The disturbance travels. The medium stays where it is. And what we measure when we detect a particle is the moment that disturbance interacts with our detector strongly enough to leave a mark. And here's the consequence I think is genuinely beautiful, and that I want you to sit with for a moment. Every electron in the universe is identical, not similar, not very alike, identical. They have exactly the same mass, exactly the same charge, exactly the same magnetic moment. Why? Because there is only one electron field. Every electron that has ever existed, the ones inside your body right now, the ones inside the sun, the ones inside a star, will never see 12 billion light years away. Every single one is a ripple in the same underlying structure. They're not copies, they're instances of one thing. Now think about what this picture means for empty space. If fields are everywhere, and if quantum mechanics says that no field can ever sit perfectly still, that's the uncertainty principle applied to fields, then empty space is a contradiction in terms. You can have a region with no particles in it. You cannot have a region with no fields. The fields are still there. They're still humming with low-level activity. They're still vibrating at the lowest energy state allowed by quantum mechanics. We have a name for this. We call it the quantum vacuum, and it is not nothing. Every cubic centimeter of empty space, according to the theory, is alive with activity. Pairs of virtual particles flickering in and out of existence, too quickly to be detected directly, but slow enough to leave measurable fingerprints on real particles passing through. The vacuum is a structured medium, a frothing, restless ocean of field activity. And the electron's magnetic behavior, the calculations we've been talking about, the muon precession experiments, all of it is essentially us measuring how real particles interact with this hidden ocean of virtual activity in the supposedly empty space around them. This isn't speculation. The Casimir effect, where two metal plates placed close together in a vacuum experience a measurable attractive force purely because of the way they constrain the vacuum's activity between them, has been verified in the lab. The Lamb shift in hydrogen is a direct consequence of the electron interacting with vacuum activity. The anomalous magnetic moment of the electron, the 12 decimal place miracle, is fundamentally a measurement of how a single electron spin gets nudged by the seething sea of fields around it. The vacuum being alive is one of the most experimentally confirmed predictions in all of science. So picture where we are now. Reality, at the deepest level our theories currently describe, is not a collection of particles bouncing around in empty space. It's 17 overlapping fields filling the entire universe, with what we call matter being patterns of disturbance rippling through them, and what we call empty space being the same fields humming quietly at their lowest energy. That's already a strange picture. It's already deeply unfamiliar to anyone who hasn't studied physics in detail. And here's the thing I want to plant in your mind for the rest of this video. If reality at the level we can currently describe is already this layered, already this rich, already this textured with hidden activity, then maybe quantum field theory is itself just the first hint that there are even more layers below. Maybe the field picture isn't the bottom. Maybe it's the floor of one story of a building that goes down further than we have ever managed to look. Because if it isn't the bottom, that would explain something. It would explain why the theory's predictions for empty space fail by a factor of 10, followed by 122 zeros, while its predictions for the electron are right to the width of a hair across a continent. It would explain how the same equations can be the most accurate and the most catastrophically wrong description of nature, simultaneously, depending on what you point them at. But to see why, we have to talk about the worst prediction in the history of science. We have to talk about the cosmological constant problem, and we have to face the fact that, by the lights of its most successful theory, the universe should not exist. Part 6. The number that breaks reality. We've been circling the vacuum for a while. Let me bring it into the center of the frame, because what quantum field theory predicts about the energy of empty space is not just a numerical embarrassment. It is the largest disagreement between any theoretical prediction and any measurement in the entire history of human science, by a margin so vast that there's nothing else in the same universe of being wrong. Here's the calculation. Every quantum field has what's called zero-point energy. It's the energy the field has even when it's in its lowest possible state, because quantum mechanics forbids it from being perfectly still. If you sum the zero-point energies of all the fields in the standard model, the electron field, the photon field, the quark fields, all of them, and you do it the most natural way, integrating over all the modes of vibration up to the highest energy scale physicists think makes sense, you get a number for the energy density of empty space. That number is enormous. Estimates vary depending on where exactly you place the cutoff, but a typical value is around 10 to the 113th joules per cubic meter. Pick a different cutoff, you can shave off a few orders of magnitude, but you're still looking at numbers that dwarf anything humans have ever encountered. Now here's the comparison that makes physicists wince. We can actually measure the energy of empty space. We've been doing it since 1998, when astronomers studying distant supernovae discovered that the expansion of the universe is accelerating. Something is pushing space itself apart, and the only consistent explanation within general relativity is that empty space has a small positive energy density of its own. We call this measured value the cosmological constant, and the measured value, after decades of refinement using cosmic microwave background data, supernova observations, and galaxy surveys, comes out to about 10 to the negative 9th joules per cubic meter. Compare those two numbers. The prediction, the measurement. The gap between them is roughly a factor of 10, followed by 122 zeros. I keep saying this number because I don't think any human brain can really hold it. There are about 10 to the 80 atoms in the entire observable universe. The error in the vacuum energy prediction is 42 orders of magnitude bigger than the total number of atoms in everything we can see. If the universe were a haystack, this error would be a haystack 10 to the 42 times bigger than the universe itself. Physicists have a name for this. Some call it the vacuum catastrophe. The more diplomatic ones call it the cosmological constant problem. Either way, it is the worst prediction ever made by anyone, ever, anywhere. And here's why it's much worse than just an embarrassment. If the prediction were right, if empty space really did have an energy density anywhere close to what quantum field theory naively says it should, the universe could not exist, not in anything like its current form. The energy of empty space pushes space itself apart, accelerating its expansion. With the predicted value, the expansion would be so violent that no two atoms could ever stay near each other long enough to form anything. No galaxies, no stars, no planets, no chemistry, no life. The universe would have torn itself into a thin uniform haze in less than a fraction of a second after it began. There would be no us, no you watching this, no me writing this. There would be nothing. Yet here we are. The universe is full of structure. Stars burned for 9 billion years before our solar system formed. Atoms hold themselves together. Galaxies cluster together in vast filaments stretching across the cosmos. The expansion of space is real, and it is accelerating, but it's gentle. So gentle that almost the entire history of cosmic structure had time to play out before it really started to matter. So one of two things must be true. Either quantum field theory's calculation is missing something fundamental, or there is some hidden mechanism that almost perfectly cancels the predicted value down to the tiny one we observe. Almost certainly, both. There must be some piece of physics, sitting at a deeper level than quantum field theory, that performs an extraordinary cancellation, leaving behind only the small residual that the universe actually shows us. Nobody knows what that mechanism is. Nobody can derive the observed value from first principles. Nobody has even come close. And the cancellation itself, if you take it seriously, is the most precise and finely tuned event in the known universe. The various contributions from quantum field theory, individually each enormous, have to cancel each other out to roughly 1 part in 10 to the 122nd power. That's more precise than any measurement ever made. More precise than any calculation ever performed. More precise than anything in nature has any right to be. And it happens for free. Every cubic meter of every part of the universe, all the time, with no apparent mechanism producing it. Pause for a second on that. The most precise thing in the universe is a cancellation that nobody can explain, sitting inside a calculation that nobody can derive, producing a value that allows you and me to exist. You can see why physicists started using words like fine-tuning decades ago, and you can see why many of them quietly began to suspect that something deeper had to be going on. Because that's what fine-tuning means in physics. It means a value so suspiciously precise that the existence of the value itself becomes a piece of evidence. Evidence that the surface theory you're working with isn't telling the whole story. Evidence that there's a deeper structure underneath, doing the cancelling, hiding the mechanism, leaving behind a tidy residue without explaining where the tidiness came from. Now hold this thought, because we're about to put two pieces of the puzzle next to each other. Quantum field theory gets the electron right to 12 decimal places. Quantum field theory gets the vacuum wrong by 10, followed by 122 zeros. These two facts sitting beside each other are the entire shape of the mystery, because no fundamental theory should produce both of those. A real bedrock of physics should be either right everywhere or wrong in clean, identifiable ways. Quantum field theory is neither. It's spectacularly precise where we can probe it directly. It's catastrophically wrong where its predictions reach into regions we can't probe directly. And that pattern, precise where probed, wrong where invisible, is exactly the pattern you'd expect from a theory that isn't fundamental at all. It's the pattern of a layer. Part 7. The idea that rewrites physics. In 1971, a physicist named Kenneth Wilson published a series of papers that quietly rewrote the foundations of theoretical physics. He didn't intend to. He was working on a completely different problem. The problem of phase transitions, like the way a magnet abruptly loses its magnetism when you heat it past a certain temperature, or the way water and steam become indistinguishable at the critical point. These problems involved physics happening at many different size scales at the same time, and the standard tools were producing nonsense answers. Wilson developed a technique he called the renormalization group. The idea was to systematically track how a physical system's behavior changes as you zoom in or zoom out, as you describe it at different scales of length and energy. And what he discovered, almost by accident, is one of the deepest patterns in nature. Physics is organized by scale. The behavior of a system at one scale of distance or energy is determined by its own effective laws. Those laws can be very different from the laws governing the same system at a different scale. Even though ultimately the same underlying physics is doing all the work, the rules that emerge at the macroscopic level can be utterly different from the rules at the microscopic level. Zoom in, and you see new structure, new degrees of freedom, new kinds of behavior. Zoom out, and the microscopic details get averaged away. What survives is a simpler description, with fewer parameters, that captures only what matters at the larger scale. For Wilson's original problem, this insight was a revelation. It explained why a magnet near its critical point and a fluid near its critical point, two completely unrelated physical systems made of completely different things, show identical mathematical behavior. The microscopic details are washed out. What remains is determined entirely by symmetries and large-scale features. He won the Nobel Prize in 1982 for this work. But the insight was much bigger than phase transitions. Once you applied Wilson's perspective to quantum field theory, the entire framework looked different. Suddenly, all the mysteries we've been talking about, the infinities, the renormalization procedure, the asymptotic series, even the cosmological constant problem, stopped looking like defects. They started looking like clues. Specifically, clues that quantum field theory was never meant to be a complete theory of nature. Here's the new picture. When you write down a quantum field theory and start calculating, you are implicitly choosing a scale. You are saying, I will describe physics at energies up to such and such, and I will not concern myself with what happens at higher energies. The infinities that appear in your calculations are exactly what you'd expect if there's real physics happening at those higher energies that you've ignored. The infinities aren't a sign that your theory is broken. They're a sign that your theory is incomplete in a specific, well-defined way. They represent the fact that you don't know what's happening above the energy scale you've chosen, and that ignorance has to leak in somewhere. Renormalization isn't a shell game anymore. It's the procedure by which you absorb your ignorance about the higher energy physics into a few measurable parameters, like the electron's mass and charge, and then proceed to make predictions at the energies you actually care about. You're not pretending the high-energy physics doesn't exist. You're acknowledging that it does, and you're using the structure of the calculation to package its effects into numbers you can read off the lab bench. The bare parameters that produce infinities are the parameters of an unknown deeper theory expressed in a clumsy language. The measured parameters are what you actually see when you do experiments at lab-accessible energies. Both descriptions are correct. They're describing the same physics from different scales. This is called effective field theory, and once you accept it, quantum field theory takes on a completely new identity. It is not a candidate for the final theory of nature. It cannot be. By construction, it is a low-energy approximation, valid up to some scale where new physics must take over. Above that scale, the description must break down. At the very highest energies, the so-called Planck scale, where quantum gravity becomes important, quantum field theory must give way to something deeper. That something might be string theory. It might be loop quantum gravity. It might be something nobody has thought of yet. But quantum field theory itself, in this view, is simply the best effective description of physics at the scales where humans have ever conducted experiments. And every layer below it is similarly effective relative to the one beneath. The whole architecture of physics, in this view, is a tower of nested approximations. Newtonian mechanics is a low-energy, low-velocity approximation of Einstein's relativity. Classical electromagnetism is the classical limit of quantum electrodynamics. Quantum electrodynamics is part of an effective field theory that breaks down at very high energies. And whatever sits at the very bottom of the tower, if anything sits at the very bottom of the tower, is something we haven't reached yet. Notice what this picture does. Suddenly, the success of quantum field theory at low energies makes complete sense. Effective theories are designed to be accurate at the scales they're built for. The 12 decimal places of agreement aren't suspicious anymore. They're exactly what you'd expect from a well-calibrated, effective description of low-energy physics. And the cosmological constant catastrophe also makes sense. It's exactly what you'd expect when the surface theory tries to make a prediction about something, the energy of empty space, that depends crucially on the deeper physics it can't see. The success and the failure aren't contradictory. They're two sides of the same coin. They're both signatures of a theory that's an effective layer rather than a fundamental description. This insight has been slowly seeping into physics since the 1970s. It's now, finally, the mainstream view. Quantum field theory is a layer. It sits on top of something deeper. We can see the layer clearly. We can probe it to extraordinary precision. We can use its predictions to build technologies and fly probes to the outer planets and split atoms and run colliders. But we cannot see directly what's underneath. We can only read its texture, its symmetries, its successes and failures, and try to infer what kind of structure could produce them. And once you internalize this picture, every other strange feature of modern physics starts to fall into place. Part 8. The Tower of Descriptions. I want to walk you up and down the Tower of Physics because I think it makes the layered idea concrete in a way that abstract talk can't. At the very top, the layer where you and I spend our entire lives, there is the macroscopic world. Solid objects, liquids, gases, the physics of cars and weather, and human bodies and oceans and planets. This layer is described, with extraordinary success, by classical mechanics, classical electromagnetism, and classical thermodynamics. Newton's laws, Maxwell's equations, the equations engineers use to design bridges, and the equations meteorologists use to forecast hurricanes. This layer is real. The laws governing it are accurate within their range. You can land a probe on a comet using these laws. You can predict a solar eclipse 1,000 years in advance. The classical picture is not wrong, it's correct, at the scales it was designed for. But zoom in, past the millimeter, past the micrometer, past the nanometer. Eventually you reach the world of atoms and molecules, and the classical picture starts to fall apart. Electrons don't orbit nuclei in clean little circles like planets around a sun. They occupy probability clouds. Energy isn't a continuous flow. It comes in discrete chunks called quanta. Identity itself becomes weirdly fuzzy at this scale, with two electrons being literally indistinguishable in a way no two macroscopic objects ever are. The certainties of the classical layer dissolve into the probabilistic structure of quantum mechanics. And from quantum mechanics emerges all of chemistry. Every reaction, every molecule, every functioning cell of every living thing. That's the second layer. Zoom in further, past atoms, past nuclei, into the world of quarks and gluons and electrons and neutrinos. Quantum mechanics by itself is no longer enough. You need it combined with Einstein's relativity, packaged into the full machinery of quantum field theory. This is the third layer, the layer we've been talking about for hours now. The Standard Model, 12 decimal places, the Higgs field giving mass to particles, the strong, weak and electromagnetic forces all unified under one mathematical framework. Now look upward in the other direction. As you zoom out from the quantum layer, microscopic details get averaged together and new effective laws emerge. The entire field of thermodynamics, the laws of entropy, heat, temperature, is an emergent description that arises from the underlying motion of countless molecules. You don't need to track the quantum state of every air molecule in your room to predict whether the room will heat up or cool down. You just need a few macroscopic variables, pressure, volume, temperature, and a handful of laws relating them. The microscopic details get absorbed. What survives is a clean, useful, simple description of what matters at the larger scale. This pattern repeats itself everywhere in science. Chemistry is, in some sense, an effective theory of underlying quantum mechanics. Biology is an effective theory of underlying chemistry. Sociology is an effective theory of underlying psychology. Each layer has its own laws, its own concepts, its own valid range. Each layer is connected to the layer below by some kind of averaging procedure, but each layer can be developed and used without fully understanding the layer below. This is one of the deepest features of how nature is described. Reality, as far as our theories can tell us, is layered. Each layer is real in the sense that the laws at that layer accurately describe the phenomena there. Each layer is incomplete in the sense that, to understand why those laws have the form they do, you have to descend to a deeper layer. Now here's the question that has kept physicists awake at night for decades. Does the tower have a bottom? Is there some final layer at the very base? Some fundamental description that isn't itself effective relative to anything deeper, that doesn't sit on top of any further structure, that just is the truth in some absolute sense? Or does the tower go down forever, with every layer being effective relative to a deeper one, in an infinite regress that has no natural stopping point? Quantum field theory cannot answer this question. From inside the framework, you cannot even properly ask it. All you can see is the layer you're in and the strong suggestion that something exists beneath it. The deeper structure, if there is one, is not directly visible to you. You can only read the texture of your own description and try to infer. And the texture says, there's something else. The cancellations, the fine tunings, the asymptotic series, the renormalization procedure, the cosmological constant problem, the failure to include gravity, all of it points downward. All of it whispers that there's another layer and then probably another and possibly another after that. What's down there? Part 9. the candidates for what's underneath. If quantum field theory is an effective description, then what is it an effective description of? What kind of structure could exist at scales smaller than anything humans have ever directly probed, and produce quantum field theory as its low-energy approximation? Several candidates have emerged over the last 50 years. None of them have been experimentally confirmed. All of them are mathematically demanding, conceptually radical, and deeply contested within the physics community. But they share a common goal: to describe what's underneath. The most famous is string theory. The basic idea is breathtaking in its simplicity. Instead of point-like particles, the fundamental entities are tiny vibrating strings of energy. Different vibrational modes of a single string correspond to different particles. An electron is a string vibrating in one pattern. A photon is a string vibrating in another. A graviton, the hypothetical particle that would carry the force of gravity, emerges almost automatically from the mathematics, which is why string theory has been the leading candidate for a unified theory of all forces, including gravity, for decades. The mathematical structure that emerges is so rich that it forces gravity to exist. You can't write down a string theory without gravity falling out of it. But string theory comes at a cost. The mathematics requires extra dimensions of space, 6 or 7 of them, depending on the version, beyond the 3 we live in. These dimensions have to be curled up into tiny configurations, far smaller than any experiment has ever probed, in order to be invisible to us. The theory has produced an enormous landscape of possible solutions, possibly 10 to the 500th distinct vacuum states, with no obvious way to identify which one corresponds to our universe. And the energy scale at which strings would become directly visible is vastly higher than anything any conceivable particle accelerator could ever reach. String theory is mathematically magnificent, conceptually revolutionary, and, after decades of effort, still untested. A different candidate is loop quantum gravity. Where string theory tries to extend particles into strings, loop quantum gravity tries to quantize space-time itself. In this picture, space is not a smooth, continuous fabric. It is a network of discrete loops or knots, with area and volume coming in tiny, indivisible chunks, the way energy comes in quanta. Loop quantum gravity makes specific predictions about what should happen in extreme gravitational situations, like the center of a black hole or the first instant of the Big Bang. Where general relativity predicts a singularity, a point of infinite density, loop quantum gravity predicts a finite, granular structure that smooths the singularity out. The theory is mathematically rigorous and produces a clean quantum description of gravity. It also, like string theory, sits well beyond direct experimental verification. There are other candidates. Causal set theory, where the fundamental entities are not particles or strings or fields, but discrete causal events with a partial ordering, a network of this came before that relationships from which space-time itself emerges. The holographic principle, partly inspired by the entropy of black holes, which suggests that the information content of a region of space might actually be encoded on its lower dimensional boundary, the way a 3-dimensional hologram is encoded on a 2-dimensional surface. Asymptotic safety, an approach that tries to rescue quantum field theory from itself by finding mathematical fixed points where the theory remains well behaved at arbitrarily high energies. Each of these frameworks tries, in its own way, to provide what's underneath quantum field theory. Each tries to handle the infinities, unify the forces, explain why the constants of nature have the values they have, produce a deeper layer that yields quantum field theory as a low-energy approximation. Each is mathematically rich. None has produced a single decisive experimental signature that would let physicists choose between them. The honest summary is this: we don't know what's underneath. We have hints. We have constraints. We have several mathematically beautiful guesses. The data so far have not been able to push us decisively toward any of them. And there are wilder hypotheses too. Some physicists and many philosophers have entertained the idea that the deeper structure might not be physical at all in the conventional sense. The simulation hypothesis, the proposal that what we experience as physical reality might be the output of some computational process running in a substrate we can never access, sits at the most speculative edge of this conversation. As a serious scientific claim, it is essentially impossible to test, because any simulation good enough to produce conscious observers like us would presumably look indistinguishable from a non-simulated reality. Most physicists don't engage with the simulation hypothesis as physics. They engage with it, when at all, as philosophy. But even the simulation hypothesis taps into an intuition that mainstream physics increasingly shares. The intuition that quantum field theory feels computed, that its symmetries, its cancellations, its fine-tunings all hint at a generative process behind them. Whether that process is literal computation in some hidden substrate, or an emergent pattern from a deeper physical theory, or something we don't yet have the vocabulary for, the underlying intuition is the same. There is something underneath, something we have not seen and may never directly see, but whose existence is increasingly clear from the texture of the layer above it. Part 10. Why the theory keeps refusing to break. I want to come back to something I said near the beginning, because I think it's the single most important and counterintuitive idea in all of this. The fact that quantum field theory keeps holding up under experimental tests, that no anomaly survives long enough to break it, that every precision measurement matches its predictions to absurd accuracy, that the muon G-2 anomaly closed, and the proton radius puzzle resolved, and the B-Meson decay anomalies kept evaporating, this is not evidence that quantum field theory is fundamental. Most people, hearing about a theory that just keeps being right, would conclude that the theory must be the truth. That's the natural intuition. If a description keeps passing every test, it must be describing reality at the deepest level. The layered interpretation says the opposite, and once you see why, you can't unsee it. The empirical success of quantum field theory is evidence that the deeper layer of physics is far away, that the scale at which the underlying structure becomes visible is so much higher in energy than anything we can currently probe, that the deeper layer barely intrudes on our experiments at all. The theory isn't holding up because it's true at the bottom. It's holding up because the bottom is far enough below us that it can't disturb the surface. Imagine if the deeper physics were close in scale to what we can probe. We would expect to see deviations, anomalies that didn't close, new particles showing up where the theory predicts none, patterns that persisted through better and better measurements rather than dissolving under them. The standard model would have visible cracks that widened as we looked harder. Instead, what we see is a remarkable, almost suspicious cleanness, a stability that gets reinforced every time we probe it, an agreement between theory and experiment that becomes more impressive, not less, as the precision improves. That is exactly what an effective theory looks like. When the underlying physics is far away in scale, the cleanness is the signature. The stability is the fingerprint of separation. We are not seeing the theory hold up because nothing is below it. We are seeing the theory hold up because whatever is below it is too far away to leave detectable traces in our current experiments. This reframing has a strange and slightly unsettling consequence. It means physics, in a sense, has been finding its own limits while looking like it's been finding answers. The more accurate quantum field theory's predictions become, the more confident we can be that it's a well-calibrated effective description. The more confident we can be that it's a well-calibrated effective description, the less confident we can be that we're approaching the bottom layer of physics. Precision is not the same as fundamentality. A perfect map of the surface of the ocean tells you a great deal about the surface and very little about what's underneath. The patterns of waves, no matter how exquisitely they're charted, do not directly reveal the shape of the seabed. You can study the surface forever and learn enormous amounts about it, and your knowledge of what's beneath the surface can still be almost entirely shaped by inference rather than direct sight. That's where physics is right now with quantum field theory. We have a beautifully calibrated map of the surface. The map is so accurate that, in places, it agrees with reality to the width of a hair across a continent. And the map itself, by the very precision of its agreement, is telling us that there is more to the territory than we are seeing. The depths recede as we approach them. The clearer the surface gets, the more obvious it becomes that the surface is not the territory. I think this is one of the most underappreciated insights in modern science. It's not the kind of thing that fits in a tweet. It's not a discovery in the traditional sense. There's no new particle, no new force, no new image of a cosmic phenomenon. What's been discovered slowly over the last 40 or so years is something about the nature of physics itself, about what kind of knowledge our best theory actually provides, about how to read the silences and the cancellations and the suspicious successes alongside the spectacular accuracies. Physics has spent most of its history finding new objects, new planets, new elements, new particles, new cosmic phenomena, object after object added to the inventory of what the universe contains. And those discoveries are still happening. They're still important. But fundamental physics, especially over the last few decades, has also become something else. It's become the science of mapping its own limits, of reading the structure of its own descriptions and learning from that structure things about reality that no individual experiment could tell us. The discovery isn't a thing you can hold or photograph. The discovery is the recognition that quantum field theory has been telling us, in the language of its own equations, that it is not the final word, that something deeper exists, that the surface we've been looking at is in fact a surface, and once you see that, you can't unsee it. Part 11. What reality might mean if this is true? If the layered interpretation is correct, and increasingly the consensus among working theoretical physicists is that it is at least roughly correct, then it does something quite radical to our intuitive concept of what reality fundamentally is. We are used to thinking of reality as made of stuff, objects, things, particles, fields, solid, definite, locatable items that exist independently of anything else. Pick up a stone. The stone is made of molecules, the molecules are made of atoms, the atoms are made of subatomic particles, the particles are excitations of fields. Each step down in the traditional view brings you closer to the real building blocks. The fundamental layer at the bottom of the hierarchy would be the layer of the most basic stuff. Find the bottom, find the ultimate furniture of the universe. That's the dream that has driven much of human inquiry for thousands of years, from the ancient Greek atomists to today's particle physicists building accelerators in tunnels under Europe. The layered picture suggests that this might be the wrong metaphor entirely. Reality, in this new picture, is not so much a collection of objects as a structure of approximations. The layers of physics aren't progressively smaller stacks of stuff. They're progressively better descriptions of something whose ultimate nature might not be object-like at all. Each layer is a way of describing the layer below. Each layer has its own concepts, its own laws, its own vocabulary for talking about what exists. The macroscopic layer talks about rocks and rivers. The chemical layer talks about molecules and bonds. The quantum field layer talks about excitations and symmetries. Each of these vocabularies is real, in the sense that it accurately captures the regularities at its scale. But none of them on their own is the final story. Reality in this view is less like a building made of bricks and more like a series of nested maps, each one more detailed than the last, with no guarantee that there is an actual unmapped territory at the bottom. We're used to thinking of maps and territories as separate things. The map describes the territory, and the territory exists independently of the map. But what if, in physics, the territory itself is just another map relative to a deeper one? What if every layer that looks like territory from above turns out to be a map when you zoom into it? You never reach the territory, you just keep finding more maps. And the question of whether there's some final territory somewhere underneath all the maps becomes a question physics may not be equipped to answer. If you take this idea seriously, it changes what several traditional questions about physics even mean. What is a particle, really? In the layered picture, a particle isn't a fundamental object. It's a localized excitation of an effective field that itself emerges from a deeper structure that probably emerges from something deeper still. The particle is a useful concept at one layer of description. It's the right way to think about reality at the scales where particle physics experiments operate. It does not have to be the fundamental thing in the universe. The whole notion of fundamental thingness might simply not apply once you go deep enough. What are the laws of physics, really? In the traditional view, the laws are eternal, absolute truths inscribed somewhere outside reality, governing the behavior of stuff from above like a kind of cosmic legislation. The layered picture says no. The laws are not eternal. They're not absolute. They're effective rules that emerge at certain scales, constrained by symmetries and consistency conditions, valid within their domains, breaking down outside. The laws are real in the sense that they accurately describe phenomena, but they may themselves be surface features of something deeper. Just as the laws of thermodynamics are surface features of the underlying molecular dynamics, there are no thermodynamic laws independent of the molecules. The laws emerge from the collective behavior. The laws of quantum field theory may emerge in just the same way from whatever is underneath, with no ultimate cosmic legislation behind them. What is an observer, really? This might be the strangest implication of the whole picture. In the layered view, an observer is always inside one of the layers. The observer is a structured pattern that emerges within a layer, looking at other patterns within the same layer, sometimes making inferences about deeper layers based on what the surface patterns reveal. You and I, sitting here thinking about quantum field theory, are patterns at the macroscopic layer. The neurons firing in our brains are patterns at the chemical layer. The molecules making up the neurons are patterns at the quantum mechanical layer. We are not standing outside the system. We are inside it, all the way down. There is no privileged outside view. There is no platform you can step onto from which to see all the layers at once. Every measurement, every experiment, every theoretical insight happens from within some layer. We cannot escape into a metaphysical observation deck and look at reality whole. The unification of all forces, if it's ever achieved, will be an internal unification. Patterns inside the system describing other patterns inside the system. The discovery of the deepest layer, if there is one, will happen from within whatever layer we currently inhabit. We will never be able to step outside reality and see it from outside. Now, this can sound a bit unsettling, so I want to be careful about what it does and doesn't imply. Saying that physics is an internal map drawn from inside the territory does not mean physics is fake or arbitrary or culturally constructed in the dismissive sense some people use the term. The descriptions we have are true. They predict observations, they capture real regularities, they let us split atoms and reach distant planets and design medicines. Truth in this picture is a property of layers. A description is true at its layer if it captures the regularities of that layer. The deeper question, whether any single layer is the real one, the one that exists most, or counts most, or matches reality in some absolute sense, becomes harder to even formulate. The question may not have a meaningful answer. And that's all right. The descriptions still work. The layers are still real. What does the layered picture mean for the human project of trying to understand the universe? It means the project doesn't necessarily end. There's always another layer to look for. There's always another approximation to refine, another set of regularities to map, another piece of structure to describe. The dream of a final theory, a single equation that closes the book on physics, becomes harder to take literally. The universe might not have a bottom. It might just be layers all the way down in a regress that has no natural stopping point. Or, if there is a bottom, it might be permanently inaccessible to us, hidden behind energy scales we can never reach with any conceivable technology, or behind logical gaps we can never bridge with any conceivable mathematics. Physics, in this view, is not a march toward a finish line. There may be no finish line. There is only the steady, patient, beautiful process of building ever more refined maps of a territory whose limits we cannot fully see. And honestly, when I sit with that long enough, the lack of a final answer stops feeling like a failure. It starts feeling like an invitation. The universe is bigger than any final theory could ever capture. That is somehow the most reassuring thing of all. Part 12. The final contradiction. We've reached the place we set out for at the very beginning. I want you to take a breath here, because what we're about to look at is not just a summary. It's the actual shape of the contradiction modern physics is asking us to live with. Quantum field theory is the most precise framework in the history of science. It produces predictions accurate to 12 decimal places. It has been confirmed by experiment after experiment over decades of increasingly sophisticated tests and never falsified by any direct measurement in any energy range we can currently reach. Every collider ever built, every precision experiment ever conducted, every measurement of every fundamental particle, they all agree with the theory, sometimes to absurd levels of accuracy, sometimes only after years of refining the calculations and the measurements until the two sides finally met in the middle. The track record is essentially unblemished within the regime we can probe. It is also a framework whose mathematical foundation includes a theorem proven 70 years ago and never overturned, demonstrating that its standard formulation of interactions is technically inconsistent, a perturbation series that diverges if you take it too seriously, a renormalization procedure that the man who invented it called, in print, a shell game, a prediction for the energy of the vacuum that, applied straightforwardly, is wrong by a factor of 10 followed by 122 zeros, the largest theoretical error ever recorded by humans in any branch of any science. A foundation that includes an unsolved million-dollar problem sitting open at the Clay Mathematics Institute since the year 2000, still unclaimed. Both of those things are true at the same time. And I want you to actually hold them in your head together for a moment, because the cognitive dissonance is the entire point. Perfect predictions and broken foundations. Empirical triumph and mathematical incompleteness. The most successful theory in the history of human thought and the most clearly unfinished one. The most accurate description of the universe ever produced, sitting on a base that mathematicians cannot fully verify and that physicists openly admit is provisional. This is the paradox we set out to face when we started. I don't have a magic resolution. Nobody does. What we have is a way of making the paradox cohere, and that's what the layered interpretation provides. It dissolves the contradiction without making it go away, which is a strange thing for a resolution to do, but it's the most honest one available. The successes of quantum field theory are explained by the theory being a well-calibrated, effective layer, with symmetry constraints so tight that they almost completely fix the form of the predictions at the scales where the theory operates, regardless of what's happening below. The deeper physics is washed out by the layering. The surface predictions come out right because the symmetries leave essentially no room for them to come out any other way. And the theory is built around respecting exactly those symmetries. The failures are explained by the theory being only a layer, with deeper physics required to handle the regimes where the layer breaks down. The cosmological constant problem becomes a signal of the deeper layer, a place where the surface description simply cannot account for what's happening, because the underlying structure is doing the heavy lifting. The renormalization mystery becomes a feature of how layered descriptions work, a natural consequence of integrating out high-energy physics you don't have access to, rather than a defect in the formalism. The asymptotic series becomes a property of perturbation theory in any effective description, not a unique flaw in this particular one. The whole picture starts to make sense as soon as you stop expecting quantum field theory to be the final word and start treating it as the most accurate intermediate description we have ever managed to construct. But notice what this resolution costs us. I want you to feel the weight of this, because it's the part physicists themselves often have a hard time saying out loud. It costs us the dream of completion. It costs us the idea, dear to physics for centuries, that we are converging toward a final theory that closes the book on reality. For most of the 20th century, the project of fundamental physics had a clear endpoint in sight. Find the theory of everything. Write down the equation that explains every other equation. Reach the bottom of the explanatory ladder and stand there. Finally, finished. The layered interpretation says that endpoint may not exist, or, if it does, we may not be able to get to it from where we are. The more we understand, the more we realize that what we know is a layer. The more confident we become in our predictions, the less confident we can be that our predictions describe the deepest structure of nature. Because the very precision that makes us confident is precisely the kind of precision you'd expect from a well-calibrated, effective theory whose deeper workings are far away. Physics is not completing itself. Sit with that sentence for a second. Physics is not completing itself. It is compressing reality more and more efficiently into effective descriptions, while the underlying machinery that produces those descriptions remains hidden. Each new theoretical advance is a better compression, a more elegant summary, a tighter fit between symbol and observation. But the underlying structure those compressions are summarizing is not getting any closer to direct view. The success is not a sign that we are reaching the end. The success is a sign that we have built an extraordinary interface to a part of nature whose deeper workings remain dark. We can interact with the interface. We can use it to predict, to build, to explore, to confirm. But the interface is still an interface. There is something on the other side of it. And the better the interface gets, the more it reminds us that there's still another side. We do not know what's on the other side, and we may not know for a very long time. We may, in the end, never know directly. That is not a comfortable thing to say at the end of a documentary about physics, but it is the most truthful thing I can offer you. Part 13. Closing the layer we cannot escape. We started this conversation with one number, the width of a hair across a continent, the precision with which quantum field theory predicts the behavior of a single electron. We're ending with another number, 10 followed by 122 zeros, the factor by which the same theory fails to predict the energy of empty space. In the gap between those two numbers lies the entire shape of modern fundamental physics. Everything we've talked about, the renormalization controversy, the Yang-Mills problem, the Hague theorem, the asymptotic series, the cosmological constant catastrophe, the closing of the muon anomaly, the Higgs being found exactly where it was supposed to be, the standard model swallowing decades of experimental challenges without showing a crack. All of it sits in that gap. And the recognition slowly, reluctantly emerging over the last several decades, is that the only way to make sense of both numbers at once is to stop thinking of quantum field theory as the final word about reality, because no final theory should produce both of those numbers. A real bedrock of physics should be either right everywhere or wrong in clean, identifiable ways. Quantum field theory is neither, which is the strongest evidence we have that it is not the bedrock at all. It is not the final word. It is perhaps an extraordinarily eloquent middle word, a description that captures something true about the world at a particular scale, with a particular precision, while standing on top of a structure it cannot directly see. The middle of a sentence whose beginning we don't yet know and whose ending we have not yet read. Every experiment we run keeps confirming the description at its own level. The Higgs is found exactly where it was predicted. The muon anomaly closes after 20 years of holding open a possible doorway. The electron's magnetic moment matches calculation to 12 decimal places, year after year. The Standard Model continues to absorb every challenge thrown at it, and every careful look under the hood keeps revealing that the description, at its foundations, is not what a final theory should look like. The mathematics is too unfinished. There are too many places where rigor gives way to pragmatism. Too many techniques whose justification is, ultimately, that they work, rather than that they are mathematically clean. The cancellations are too miraculous. The way different contributions to physical observables happen to add up to small finite numbers, instead of the enormous values their individual pieces would suggest, looks less like a feature of fundamental physics and more like the fingerprint of a deeper structure quietly enforcing the cancellations from below. The vacuum is too suspiciously fine-tuned. The free parameters are too numerous and too unpredicted, with around 25 constants whose values are simply inserted into the theory by hand. The gravitational sector is too absent. The fact that we cannot include gravity in the same framework as the other forces, despite a century of trying, is itself a screaming clue that the framework is not the whole picture. So the theory keeps confirming itself empirically while quietly admitting in its own structure that it is not the bottom. The data say yes, the mathematics says wait, and we are sitting in the middle of that conversation trying to figure out what to do with both messages at once. We are stuck on a layer, and from this layer we look down into a darkness that we cannot fully see into. That is not a poetic flourish. That is a literal description of the experimental situation. Our most powerful particle, accelerator, the Large Hadron Collider, can probe energies up to about 14 trillion electron volts. The energy scale where quantum gravity is expected to become important, the so-called Planck scale, is roughly 10 to the 16th times higher than that. To probe directly the scale where quantum field theory is expected to break down and the deeper layer might become visible, we would need an accelerator the size of a galaxy. We are not going to build that accelerator, so we are reasoning from the surface, knowing the surface is not the bottom, hoping that something in the structure of the surface will reveal something about the depths. Maybe one day an experiment at some unimaginably high energy or some unimaginably precise low energy probe will lift the veil and reveal the structure underneath. Maybe a cosmological observation will pin down the cosmological constant in a way that cannot be explained without invoking new physics. Maybe a precision measurement of some subtle effect will catch the deeper layer leaking through. Maybe a new mathematical framework will achieve what string theory and loop quantum gravity have so far failed to do, and produce testable predictions that take us decisively below the quantum field layer. Maybe the deeper structure is something nobody has yet imagined, and our descendants will look back at our debates about renormalization and the cosmological constant and smile at how we missed the obvious answer. Or maybe we never reach the bottom. Maybe the bottom doesn't exist. Maybe reality is layered without end, and every layer we discover is just another approximation of a deeper one, with the regress continuing forever. No final structure, no ultimate furniture. Only an infinite sequence of effective descriptions, each one beautiful in its own right, none of them the last word. Maybe the search for the final theory is not a search for an answer at all, but a description of an activity. And the activity itself, the map-making, is what physics actually is. I do not know which of these possibilities is true. Nobody knows. Anyone who tells you they do is selling you something. But here's the thought I want to leave you with. Sit with it for a moment before the video ends. The most successful theory in the history of human thought is also, by its own internal evidence, an incomplete one. Its precision is not a sign of finality. Its beauty is not a sign of bottom. Its agreement with experiment is not a sign that we have arrived at the end of the road. It is a sign that we have built something extraordinary within its domain, and that there is more, much more, waiting to be found beneath it. We are explorers on a beach, charting the patterns of the waves with extraordinary precision, mapping every curl and every interference and every flick of foam. And underneath us lies an ocean we have only begun to suspect exists. The waves are real. The patterns we map in them are real. But the waves are not the ocean. They are the surface where the ocean meets the air. And underneath them is a depth we cannot see directly from the shore. Quantum field theory is the wave map. The ocean is whatever is underneath. And the strangest, most beautiful realization of modern physics is that the wave map itself, in the very precision with which it describes the surface, is silently telling us about the depths, the texture of the patterns, the regularities, the cancellations, the suspicious cleanness of certain calculations, and the catastrophic failure of others. All of it is information about what's below. We just haven't yet learned how to read all of it. The story of physics, then, is not a story of reaching final answers. It is a story of recognizing that every answer we find is part of a larger question we have not yet learned how to ask. Quantum field theory is the most precise and complete description of reality ever constructed, and until something better comes along, it will remain the layer we cannot escape, even as it whispers, in the very structure of its equations, that there is something else, something deeper, something waiting underneath. We will keep looking. We will keep building experiments, designing detectors, refining calculations, proposing frameworks, testing predictions. We will keep refining the layers above and the layers below. And we will keep wondering, in the late hours when the mathematics gets quiet and the data sits still on our screens, what exactly is hiding beneath the most successful theory in the history of human thought? Maybe we'll find out. Maybe we won't. But the question is the most interesting one humans have ever managed to formulate. And tonight, you and I sat with it together, in the quiet. And that, in some small way, is part of the search. The wondering itself is part of the work. Until next time, keep looking up, keep looking down, and keep wondering what reality really is, all the way down to whatever bottom it may or may not have.